We now want to put together kind of everything we have and get some guidelines for curve sketching using what we've learned about how the derivatives affect the shape of the graph and also things we know from college algebra, kind of combine those things. So for our guidelines, we are first going to start with the domain. So we need to decide if there are any excluded values and what we can use for x. That's going to make a big difference in the shape of our graph. Then we're going to look for any x and y intercepts, and we're going to look for any symmetry. And these are all things that we did in college algebra as we were looking at graphs. Let's take the function y equals x to the fourth minus 4x. First of all, for the domain, we see that we have a polynomial function. The domain is going to be all real numbers. We would look for things that were excluded from the domain if we had a rational function, a natural log, things like that. The intercepts, remember that we find x-intercepts by substituting 0 for y, and so let's do that. We can factor out an x and have x cubed minus 4 equals 0, so that means x equals 0 or x equals the cube root of 4, and we could punch buttons on that and see that that is about 1.6. So our x-intercepts are going to be at 0, 0, and at the cube root of 4 and 0. Now for y-intercepts, we would put 0 in for x, but we would get back 0, so this x-intercept is also where it crosses the y-axis at 0 as well. Now let's remember how to test for symmetry. If you have an even function, it's symmetric about the y-axis, and the test for an even function would be to put a negative x in for the x, and if once you simplify it you get the original function back, we know it is even. How that can help us graphically then is we could figure out what this right part of the graph was, and then we could reflect it about the y-axis. Now an odd function was symmetric about the origin, so if we could put a push pin here in the origin and rotate this 180 degrees or turn this upside down, this piece would land over here. For every xy on the graph there's a corresponding negative x, negative y. Remember the test for an odd function, we still put negative x in for the x, and if after simplified it is equivalent to the negative of the function, then we know we have an odd function. One other thing we'd want to look for is a periodic function. Very often if the trig function's involved in some kind of combination with things, we could get a periodic function, and if we have a function that is periodic it's going to repeat itself, so of course if we can figure out what it looked like on one period then we could continue that. Now after we find these three things, and actually the function that we had, y equals x to the fourth minus 4x, if we put a negative x in, we would get x to the fourth plus 4x, and so this one is neither even nor odd, so the symmetry is not going to help us on this one. Now let's look for asymptotes. We had ways of doing that in college algebra, but now that we know calculus and limits, we are going to officially be able to define asymptotes in terms of limits. So we know a horizontal asymptote was a line that the graph headed towards as we went out on the ends. So official definition, the limit as x approaches infinity of f of x equals L, or the limit as x approaches negative infinity of f of x equals L. Could be one or the other or both. Often it's both, but it doesn't need to be. We could have two different horizontal asymptotes, one value that it headed towards as we went to negative infinity and a different value as we headed towards positive infinity, or they could match. Now a vertical asymptote would do the limit as we approached some finite value, the function was going towards infinity or negative infinity. So as we see here, as x approaches a from the right hand side of the function we could go to infinity, or from the left hand side if the limit was infinity, or could go to negative infinity from either the left or the right. And if any of these things happen, then we say a is a vertical asymptote of the function. We also have one more kind of asymptote. It was called an oblique asymptote, probably with your college algebra. It's called a slant asymptote here, same thing. The limit as x approaches infinity of f of x minus mx plus b equals 0. If that's true, we have a slant asymptote. Well, let's see essentially what that's saying. Here we have a function, and here we have a line, y equals mx plus b. And as we go towards infinity, if the distance or the difference between those two ends up getting smaller and smaller and approaches 0, so that the limit as we go to infinity is 0, then we say it's a slant asymptote. So it is a line that the function is heading towards as x approaches infinity. So let's go ahead and look at a rational function that would have asymptotes so we can see how to apply these definitions. So first, looking at horizontal asymptotes, we would look at the limit as x approaches infinity of 2x squared minus 4x over 3 minus x squared. Well, we know how to find the limit. We could either multiply numerator and denominator by 1 over x squared and then let x approach infinity, or we could apply L'Hopital's rule because this is indeterminate infinity over infinity. Let's do that since we just learned that. So we have the limit as x approaches infinity. The derivative of the numerator is 4x minus 4 over the derivative of the denominator is negative 2x. Now if we let x go to infinity, we still have an indeterminate infinity over infinity. So we could apply L'Hopital's rule one more time. The limit as x approaches infinity, the derivative of the numerator is 4, the derivative of the denominator is negative 2. So to evaluate these limits, I'm going to be approaching from one side or the other. So let's go back and look at our function here, and we'll look at the factored version of the numerator because that will make it a little easier to see. We're going to approach the square root of 3 from the right hand side, so I'm going to have a number slightly larger than the square root of 3. If I square something a little larger than the square root of 3, I'm going to end up with a value a little larger than 3. So 3 minus something a little larger than 3, this denominator is going to be negative. Now looking at the numerator, if I put in something a little larger than the square root of 3, this factor will be positive. Something a little larger than the square root of 3, well, the square root of 3 is 1 point something, and so when I subtract these, this quantity is going to be negative. So I will have a negative divided by a negative, which is positive. So this tells me that this is going to approach positive infinity because I get a positive value as I get something approaching from the right hand side. Now let's approach from the left-hand side. So we have something slightly smaller than the square root of 3. So something slightly smaller than the square root of 3, when I square it, will be slightly smaller than 3. 3 minus something a little smaller than 3 will be positive. Something slightly smaller than square root of 3 here will be positive. Slightly smaller than square root of 3 here, by the time I subtract 2, will be negative. So positive times negative will be negative. A negative divided by a positive tells me that the limit as x approaches square root of 3 from the left hand side will be negative infinity. Now let's go check out negative square root of 3 from the right side and the left side, and then we'll go ahead and sketch our asymptote. So we're looking at something just to the right of negative square root of 3, and so that value, by the time we square it, we could even say something like, maybe the easiest way to think of this is actually get a decimal to approximate so I can show you. So the square root of 3 is approximately 1.7. So if we're looking at negative 1.7, if we picked, say, negative 1.6, by the time we square that, it's going to be positive and it will be a little smaller than 3. So when I subtract these, I will get a positive. Now, what if we put in a negative 1.6 up here? This will be negative. A negative 1.6, subtracting something else, this will be negative. So a negative times a negative will be positive, and a positive over a positive tells us that as we approach from the right, we're going to be heading towards infinity. Now let's approach from the left. So if we were at about negative 1.7, let's think of something like negative 1.8. If we take negative 1.8, by the time we square it, we will get a positive value slightly larger than 3. So 3 minus 3 will be negative. If we put a negative in here, this will be negative. A negative minus another one, this will be negative. Two negatives multiplied will give us a positive, and a positive divided by a negative is negative. So what that tells us is that as we approach negative square root of 3, it's a vertical asymptote, and as we approach from the left, we will be heading towards negative infinity. Let's go ahead and sketch these asymptotes then so we can see how this all comes together. So here we have 1 and 2 here, and if we're looking at the square root of 3, that is about right here, and negative square root of 3 is about right there. We know we have a horizontal asymptote at -2, and we know that as we go out on the ends that this graph is going to be heading towards this line. And we know we have vertical asymptotes at square root of 3 and at negative square root of 3. And we haven't yet found points on the graph, but we do know that as we approach square root of 3 from the right hand side, we would be going towards infinity, and from the left hand side towards negative infinity. And as we approach negative square root of 3 from the right hand side, we'd be going towards infinity, and from the left hand side towards negative infinity. Now the graph could be down here, up here. I'm just signifying what's going to happen. So as we go out on the end, we could be above or we could be below, but we're going to be heading towards the line y = 2, and we'll be heading towards these vertical asymptotes as we approach them from the left or the right. After we get the asymptotes figured, we are ready to look for intervals of increase or decrease. And we're going to do that by using the first derivative, because we know if the first derivative is positive, we have an increasing function, and if the first derivative is negative, we have a decreasing function. And then we can also determine local maxes and minimums by seeing what goes on in this combination. So let's go ahead and return to the function x to the 4th minus 4x, and let's find its first derivative. That's going to be 4x to the 3rd minus 4. We can factor a 4 out of that and have x to the 3rd minus 1. And then we can remember the difference of cubes. Oh, that's probably been a while. It's going to be x minus 1. This first one squared. Multiply these together but change the sign. This last term squared. Now we want to know when that equals 0, because it's never going to be undefined. This is a polynomial, and so we are going to get at x = 1. You can take this and figure out where it equals 0. It won't factor, so you'd formula it, but we don't get any real numbers there. So our only value where the first derivative equals 0 is 1, so that's our only critical number. Now we can draw a little picture here then and mark where x = 1 that the first derivative there is 0. And what we're going to do now is we're going to determine the sign of the first derivative on either side of 1. So let's start by looking at 2. This would probably be the very easiest place. What if we put in a 2 here? Of course, we get 8 minus 1. That's positive times a positive. We don't really care about the number itself. We care that it's positive. This means that the function is increasing on this interval. Let's go ahead and put in 0. If I put in 0 here, I'd have a negative times a positive, which will be negative. This means the function is decreasing on this interval. So we have the intervals of increase and decrease. The function is going to be decreasing from negative infinity to 1, and then it's going to be increasing from 1 to infinity. Oh, well then I know what's going on at 1, because if it's decreasing and then it's increasing, I know that at 1 I have a local minimum. I could find the point where this local minimum is if I take a 1 and I put it in the original function. If I put a 1 in, I'd have 1 minus 4. So at the point 1, -3, this function has a local minimum. Now let's look at what we would do for our next step, and that would be to determine intervals of concavity and any points of inflection. So we are now going to be looking at our second derivative. So let's find our second derivative. We have y = x to the 4th minus 4x. So our first derivative was 4x to the 3rd minus 4. And our second derivative is going to be 12x to the 2nd, and that's it, because the derivative of -4 is 0. If we're interested in where that equals 0, it's going to be 0 at x = 0. So let's make us a little sign pattern here, and we know that the second derivative at 0 is 0. What does the second derivative do as we move over to the right hand side if we have a 1? Well, we see the second derivative, we're going to be squaring things, so it's always going to be positive. So it's positive over here, and if we put a negative 1 in, it's still positive. Positive means concave up. So what this tells us is there was a candidate for an inflection point at 0, but it was not an inflection point because this graph is concave up everywhere. And our last step is to sketch the curve. So we're going to put all of these pieces together to see what this graph looks like. So first of all was our domain, and our domain was all real numbers, so no restrictions there. Secondly, we had our intercepts, and we had 0, 0, and we had the cube root of 4 and 0 for our intercepts. Then looking at symmetry, we didn't have even or odd functions, so we didn't have symmetry. There would be no asymptotes in this one because we didn't have rational functions or things that may have asymptotes. But one of the things we could consider, there's no vertical asymptote, but we could look to see what does this function do as we approach infinity or negative infinity, and we can see that this will just keep getting larger and larger and larger, and so it's going to approach infinity. Looking for our intervals of increase or decrease, we saw that it was going to be decreasing from negative infinity to 1, and then it was going to be increasing from 1 to infinity. Our local maxes or local mins, we found out that there was a local minimum at the point 1, negative 3. And our concavity, we found out it was concave up everywhere. So let's go ahead and put these pieces on our picture. If we draw our graph, and let's go ahead and put on some of our key points here. Let's put on our x-intercepts. 0 at 0, and if we computed the cube root of 4, it's about 1.6, so we'll put that in right here. And then we know that we are going to be heading towards infinity as we go out on the ends. We have decreasing from negative infinity to 1 and increasing from 1 to infinity with this local minimum at 1, negative 3. So let's put on the point 1, negative 3. It is concave up everywhere. So this is going to have to head up and go towards infinity. This side is also going to need to head up and go towards infinity. It's a little shaky looking there because of this tablet. But essentially this graph comes down, goes through this minimum, comes back up. It's not a parabola because it's kind of skewed. This lowest point is at 1, and so it's not totally balanced on each side, but it looks something like that. It'll be important to watch the example video so you can see each of these steps applied to various functions.